Thank you for hosting this presentation on our research conducted here at Chalmers University of Technology in collaboration with SSPA and Gothenburg University, based on the west coast of Sweden. I would like to thank our hosts and GloFouling partnerships, and of course with the support from Swedish agencies. Financing, we have developed a tool where we can calculate the environmental and economic footprint of both the fouling part and the maintenance of the hull. And as you see here, an example of a hull almost ready to sail from a dry dock. This is not always the case. When a vessel is staying idle for prolonged periods, a surface that was originally clean will become eventually fouled to a certain level. And what we mean by biofouling is just any type of marine organisms that attach to the hull. And on average, this leads to about 10% increased fuel consumption, or it's roughly the same in emissions to atmosphere from a friction penalty resulting from a rough hull. On the other hand, we operators or ship owners will resource to applying an anti-fouling coating, which will gradually release biocides to the seawater or to the marine environment. And in the case of the Baltic Sea, this corresponds to about to a sizable amount of copper emitted yearly compared to the total input to the Baltic Sea. And this, of course, will inhibit the development of fouling, as we discussed previously, but it also has an impact on the water quality of harbors and especially in enclosed seas, such as the Baltic Sea. Other options, of course, exist, such as in combination or with coatings that do not have any anti-fouling properties, such as in water cleaning. And with this project that ran from 2019-2021, we have developed a decision support tool, which we call HullMASTER. I'll get into that in a while. And the team that has developed this has a broad expertise from environmental chemistry all the way to marine biology and naval architecture, to develop a cross-disciplinary tool that allows us to look into many different impacts from the maintenance of the hull and operation of vessels. And of course, I would like to acknowledge the shipping operators that have collaborated with us, offering us their data and which come from ro-packs and tanker vessels. So why developing a decision support tool? We developed this tool with the aim of filling the gap of having an independent source of recommendations for maintenance. We see that there are many sources of information for operators, and we would like to offer a scientific or evidence-based approach to the problem of selecting the best strategy. And how we address that is to look into what we mean by strategies here is different types of coatings that are available, as well as different types of in-water maintenance or even dry docking maintenance scheduling, but that's a little more difficult to control on that side. And depending on the vessel case and the operational profile and routes, these recommendations will be, of course, tailored to a specific vessel or specific operation profile. And in the end, what we look at, what we want to achieve, is a societal, economical, and environmental costs of both the maintenance and the fuel consumption or bunker consumption and emissions. And this is, of course, of interest for ship owners from the economic part and also from the corporate responsibility part of shipping operators, also for charters and authorities with interest in climate, air quality, and water quality, which fouling and maintenance hull maintenance have an impact on. And the tool is developed as a standalone program for Windows, where a ship owner or any interested party can go in and define this vessel specifications. And as a result, this is the input part. The output part is a cost difference compared to a business as usual scenario. And this business as usual is the conventional approach of using a biocidal anti-fouling coating, emitting copper, emitting other biocides, and we use the conventional approach for the business as usual. And when we look at this plot, for instance, here, we have the amount of savings that are done from an economical perspective, but also the amount of savings that are achieved, let's say in euro per year or in dollars per year, if you would like, in the societal part, which includes climate, air quality, marine water quality. And the data sources for this program or for our models include the field testing of coatings. In this case, specific case for this tool, we have developed or we have collected data for the Baltic Sea region and also relied on previous coating tests that have been provided along the years from other studies. Besides this, we have from the coating side, the emissions that are emissions from the coatings. We have data provided by field measurements using an XRF or X-ray device to determine how much biocides are being emitted from the coatings, and so we can account for that for different seawater conditions. It's importantly to mention also the pricing part, where we collaborated with industry partners to estimate the pricing for the region we are looking at, which is the Baltic Sea region at the moment. Of course, these pricing estimates can be manually changed by the user if better pricing estimates are available, if more accurate pricing estimates. From the societal costs or environmental costs, we have other supporting research, such as this article where one of our colleagues has worked on collecting the environmental pricing of different emissions. Here's an example then how this works in practice. So here we have the Baltic Sea region, and we have panels which have been exposed both on the west coast here with higher salinity, as well as on a lower salinity. And what the message here is that for different salinities we have a much different fouling rating, and how we define the fouling rating here is as a 0 would correspond to a clean coating, and 100 would be the worst case scenario with all types of fouling developed on a certain surface area. And as you see here, for high salinity, fouling develops much quicker, reaching the highest level already at around 150 to 250 days. And here's an example photo of how that looks. For low salinity, fouling develops much slower, reaching barely a level of 20, which corresponds to soft fouling or filamentous fouling developed on that surface. Also comparing different coatings. So what we looked at here was for an inert coating, And if you look then, of course, for a copper coating, as expected, we have a much better performance where we only have slime. But surprisingly, even for a foul release coating with no biocides, these coatings seem to work quite fine even under idle conditions and even at a comparable level to an anti-fouling coating. When we do use this kind of data and correlate to how much more power is required to propel a ship at a certain speed, we look then at comparing predictions based on our models, HullMASTER, to onboard measurements. And in this plot, we have a voyage data or 10 minutes points for power at a certain speed. And what this gives us is the percentage penalty, how much more power is delivered to the propeller to achieve the same speed. And we see that that varies between a level of about 10% to 60% in some points and some averages. What is interesting to see is, of course, there's a lot of there's still significant uncertainty in the measurements from onboard measurements, but what is important to retain here is the comparison of the mean values and their statistical significance to the predictions from HullMASTER, and we see a good correlation between measured points in gray and HullMASTER predictions in blue, whereas each dry docking contributes to some improvement in the or reduction in the penalties. And once we have, in the case of this specific vessel, we have changed to an inert coating, where we see a rapid increase in powering penalty at the end of this period, which was due to a prolonged idle period. And this is well represented in the predictions from HullMASTER to a level of up to 60% penalty in this very extreme case. When we have other coatings that seem to perform better, and again, this confirms what we have from our field testing of different coatings, is that the foul release coating contributed to an immediate decrease in the penalty to almost smooth level. And I should remind again, this is a rough hull compared to a smooth hull, and a slow increase towards the last period. And this correlates quite well with what we see in the field with foul release coatings performing either similarly or better than copper coatings. And this type of validation we have performed for 9 vessels, or over our almost 40 vessel years of data, and that and by comparing the predicted power penalty against measured penalties, we see that these points match in about 85% of the cases when we compare 3-month averages before after maintenance to theirs and consider their statistical significance, represented here by error bars as 95% confidence intervals. These results will be more detailed, presented in more detail in HullPeak conference this year. An application example how our tool, our suggestion of how this tool could be useful is looking here at operator costs for different coatings, different coating types. We can then compare the cumulative costs for operators, or for this could be seen as the total cost of maintenance and bunker a long time. And we see that we can compare different coatings and see when does a break-even point happen in time. On the other hand, we can compare the totals and see how much can we save, or in this case, how much is can be assigned to a bunker penalty, how much can be assigned to maintenance costs, and then we can see where the savings can be made, if there are any savings to be made in a certain comparison. This is just an example for 130-meter general cargo, and of course these values will vary depending on many parameters. And the point with this application example is just to showcase how the tool can be used. So don't pay too much attention to specific absolute values at this point, just as an example case. From the societal costs, we have assumed different emission factors for emissions to air based on previous literature and depending on specific engine parameters. But also then we can relate that to the powering penalty, and most importantly to retain from this plot is just that we have a list of different emissions that we consider, and in this case it seems that the zinc and copper, or so the biocidal emissions, stand out in this plot, and when we move on to biocide-free coatings, those of course will be reduced to zero. In a comparison then between coatings, we have here a comparison between the fall release case and the icebreaker inert coating, and both of them are here compared to the baseline case of a biocidal antifouling coating. And what we see here is a significant saving per year for the environment, for the society and environment, when moving from an antifouling coating to a foul release coating, or when moving to an antifouling coating to an icebreaker coating, with marginal savings. And I say marginal because the confidence intervals given by the error bars are still quite significant in this case. Marginal savings or marginal expenditure from the operators to give a certain environmental and societal benefit. So as a conclusion to this brief introduction to HullMASTER, we would like then to point out that we have developed a tool that is interactive and can be tailored to different cases, vessel cases and operational profiles, and that accounts for both economic and societal costs, where the societal costs include the air quality aspect or health, impact on health, and the marine environment. The validation against vessel performance from our onboard data shows about 85% agreement for those vessels we have tested in the Baltic Sea and transition to North Sea. There are still some, of course, the foul release coatings look promising, but there are still gaps in terms of ecotoxicity. That means the impact on the marine environment of these coatings needs to be further investigated, as well as applicability to other vessel types that might, where foul release coatings might not be suitable. As future work, we would like to just point out a few items that we think are worth looking into, and that is, of course, to continue the communication with shipping operators and organize even workshops where they can have a hands-on with tool. Then we think of utilizing any of the output for improving the existing environmental scoring systems, or come up with recommendations, as well as recommendations for best practice for different segments, vessel segments, and importantly, extend the tool beyond the Baltic and North Sea. Of course, that will require that we have or that we add data for other regions outside our current working area. And then we can look at other, of course, other cost-benefit analysis for new technologies that come up, and reduce model uncertainties is of course important to be more confident that we will have such savings or benefits for the environment. I would like then to thank you for your attention and